So the question is asked, how do you find the empirical formula given you have some unknown mass and then you run a combustion reaction? So first off, it's good to understand what the empirical formula is versus the molecular formula. So I kind of like to think of the empirical formula as Lego bricks. So it's the smallest indivisible formula that you can have. So you can see we can't divide this by any more, but we can put two of the empirical formulas together and we'll get a molecular formula that is made up of the empirical formula. So the empirical formula is the smallest amount you can get, and occasionally the empirical formula will equal the molecular formula. So if we go over to our problem, we can see that some unknown hydrocarbon has X amount of carbon, Y amount of hydrogen, and could have some amount of oxygen. So I went ahead and simplified the numbers just because it doesn't really matter in this problem, because you'll see at the end we'll reduce it down to about 1 sig fig, so we don't need all these sig figs. So in order to start this problem, you have to convert everything to moles first, because moles is the only way you can really compare two things together. So we take carbon dioxide and we divide it by its molecular weight. So we got 44 grams per mole. We put that in our calculator, 1.32 divided by 44. We'll get 0.03 moles of carbon dioxide. And likewise, we can do the same thing for water, divided by 18 grams per mole, right? The molecular weight of water. So we take 0.54 divided by 18, and we'll get 0.03 moles of water. And so now we kind of can tally up things together. So we got the carbon column, we got the oxygen, and then we got the hydrogen. So for every mole of carbon dioxide, I kind of like to think of this intuitively. If you'd like, you can use dimensional analysis. But I kind of think of this intuitively. So for every mole of carbon dioxide, we'll have 1 mole of carbon. So this is a 1-to-1 ratio. So we'll have 0.03 moles of carbon, right? 1 mole of carbon dioxide gives 1 mole of carbon. And we could do the same thing for hydrogen. So every mole of water will give us 2 hydrogens. So we'll go ahead and double this. So 0.06 moles of water. And then for oxygen, we'll add both of them together. So we'll have to double this number for carbon dioxide, and this will be the same. So we'll actually be tripling this number since these two are the same. So we'll have 0.09 moles of oxygen. And so this is not oxygen, the diatomic molecule. This is the oxygen atom, right? So this is moles of O, moles of C, and moles of H. So now we're kind of stuck here. So you don't want to count the atmospheric oxygen in your molecular formula. So it just doesn't belong. So we're going to have to go ahead and add up everything. So we'll take 1.32 plus 0.54, and we'll get 1.86. So 1.86 is the amount of grams of CO2 and water. And so that's the amount of products we have. And obviously the conservation of mass, the amount of products is going to be equal to the amount of reactants. So if we go ahead and subtract our unknown that we started with, minus 0.74 grams, so we'll get 211. So we'll have 1.12 grams of atmospheric oxygen. 0.11. Oops, sorry. 2. And that way we can figure out, we could subtract this. So we're going to divide this by 16 grams per mole. So even though oxygen right here is diatomic, we want to find the amount of oxygen atoms, not the amount of oxygen molecules. So we're going to take 1.12 divided by 16, and we'll get 0.07. So this will be 0.07 moles of oxygen atoms. And then we'll go ahead and subtract that down here. So minus 0.07 moles of oxygen. So we got 0.02 moles of O. And now, so this is what our unknown is made up. It's made up of 0.03 moles of carbon, 0.02 moles of oxygen, and 0.06 moles of hydrogen. So what we do now is we want to find our coefficient. So we're going to divide by our smallest unit. So right here, it's going to be 0.02. And we want to do that in order to find 1, to get 1 as one of our coefficients. that's just going to make everything a lot simpler. So made a mistake right here. This would be a 2, and this would be 0.02. And so now we divide this and we get our coefficient as 1.5. And this would be moles of carbon. And right here, our coefficient for oxygen would be 1. And our coefficient for hydrogen would be 3. So obviously we can't have 1.5 carbons for reasons. So we're going to have to multiply everything by 2. So this becomes times 2, this becomes 3, times 2, this becomes 2, times 2, this becomes 6. So our empirical formula for this equation, which so happens to be our molecular formula as well, is C3H6O2. So you can see we can't divide this by anything smaller. So this is our empirical, but it is also our molecular. So and molecular. So when our empirical is equal to our molecular, yep, so this is the answer.